And then that's the tangent. I try the cotangent. And then for the secant, secant is basically is 1 over cosine. So find its derivative. Right, but we could flip it up. But that is the property that we have never seen yet. We don't know what to do when we flip it up. But what we could do is let the u and the v. Negative sign. That we get the derivative of secant is what? U prime times v minus v prime times u over the square of v. Right, what we get is sine of x over cosine square of x. Which it could be separated as 1 over cosine times sine over cosine. That we get is secant times tangent. And that we get secant over tangent. So try the cosecant of x. But if we don't follow this quotient rule, right, well, let's see what will happen. We should get the same secant tangent, but that is the cosine x to the negative 1 f derivative. Which we have negative 1 half there, then times cosine of x to the negative 2. If we stop at here, that we get is negative 1 over cosine square of x, that's negative secant square of x. Which is not right. So the cosine x, when we apply the power rule directly to it, that will not get the expected result. And we're sure that the quotient rule has to be correct. That's this thing, maybe we have seen, but actually we didn't see that type before. Right? What we've seen, everything was like x to the negative 1 to apply the derivative. That we get negative 1 over x squared. This is true, of course. But we have never seen that the inside is a composite function. Right? The function is a composite one, which means we have not only the power, but inside under power is not only the x, inside is the cosine of x. That we call some issue here, right? Which simply leave like that is not correct, as we have already seen. Means the inside is another function that when we take in the derivative, it's not completely done. Right? To make it completely done, we'll have formula to deal with it in the next section, right? Section 3.4. But for here, that is an issue. Right? We will try. But the formula has to be correct. We have used the quotient rule to verify it already. So try the formula, try to explain or illustrate it, or at least develop it using the quotient rule for cotangent x and for cosecant x. Try that. Right, so try to do some example. I believe you had written down the formula already. Right, so try to do that find the derivative for y equals x minus tangent of x. Right, then the derivative will be 1, right, minus the derivative of tangent is secant squared of x. Right, that's staying have also a formula to do, right? So recall that if you leave like that, it's totally fine, but recall that secant square of x plus 1 is tangent square of x. Oh no, that tangent square of x plus 1 is secant square. Sorry about that. Tangent square x plus 1 equals secant square of x, therefore secant square of x minus 1 is tangent square of x. Recall that. So when we get 1 minus secant squared, that will be negative secant square of x minus 1 is negative tangent square of x. Of course, when you simplify, you get y prime to be negative tangent square of x. That is also acceptable, but if you leave the answer like the first one, it is still also acceptable. Right? So either one is okay. Like to be a little shorter, you could write as the second one. Also find the derivative. X times cosecant of x. That we can see that this is a product. We have x times cosecant of x. That our u is x, v is cosecant of x. That u prime is 1, or v prime is the derivative of cosecant is itself and the cotangent with negative. Right? That is negative cosecant cotangent. Well, when you try to develop your formula by yourself, you may be able to remember it more clear of what it's supposed to be. Then our first path, our second path, f prime of x will be u prime times v plus v prime negative cosecant x cotangent x. Well, I always put in parentheses because that is the function of, that is the value evaluated for the trig functions, right? So usually put in parentheses around your variable. That we get is cosecant of x, negative x cosecant x, cotangent x. And not necessary to factor it out. If you want, you could try to factor out the cosecant x. That's cosecant x times 1 minus x cotangent x. But here, even factor out will not make it more cleaner. Right? So leave the f prime like that is nice enough. Right, the next one is try to differentiate means find the derivative, right? It's the verb of finding the derivative. Differentiate both forms. One minus what? Cosine of x over sine of x. That's the first format, right? 1 minus cosine over sine, which could get to the form of cosecant of x minus cotangent of x. Right, so we have two forms, right? The first form is simply apply the sine cosine as the trig function, but apply the quotient rule. The second one is the other four, like tangent, cotangent, secant, cosecant. We have cotangent and cosecant as the thing we see, right? So two forms. Right? First form, quotient. We get u to be 1 minus cosine of x. V is sine of x. U prime, that's 0 minus negative sine, which is sine of x. V prime is cosine of x. Right, that's the u and the v, u prime and v prime. That we get the f prime of x will be u prime times v minus v prime times u over the square of v. Right, that's what we get, and we're able to simplify it, right? That we get sine squared of x minus cosine of x plus cosine squared of x what we are able to get is sine squared plus cosine squared is 1. 1 minus cosine x over sine squared. One minus cosine x over sine squared of x. That's what we can get. Of course, you could simplify more to get cosecant square minus cosecant cotangent. That's also appropriate. And for the second expression, we could directly apply the formula to that. The derivative of cosecant is negative cosecant cotangent of x. And that one is negative cosecant squared of x, which we get is negative cosecant cotangent plus cosecant squared, which these are equivalent as we said before, right? So if you change everything into sine and cosine, that is negative 1 over or negative 1 over sine x, cosine x over sine x, 1 over sine x squared. Well, luckily we get sine squared as denominator, we get negative cosine x plus 1, or 1 minus cosine x. Right? These two should be equivalent. And what we get is they are equivalent. Right, so that is what we see for the derivative. I use the quotient rule, and after we divide, the same thing, right? 1 over sine x, cosine x over sine x, that's cosecant minus cotangent. What we get, either apply the quotient rule or apply the direct formula will be a little same, right? But for this question, also second thing we see is for the trig functions, right? Actually, if we're able to divide to simplify to the other format, which the remaining formats after we divide could be a little easier, then we follow that. We could actually stop there to finish our derivative, right? To finish the steps of differentiate a little easier, right? But the rest step is to just make sure that the two formats are equivalent. when we use quotient rule, it's also fine, but a little more simplification we do, right? Either way is good. You decide which one you want to do. Right, personally, I feel the second way is a little bit easier, but first way is also not that much hard, right? Same thing. Well, higher order differential derivative. We had seen, well, last time, right, the position functions. The velocity functions. And by definition, velocity is change of position. Therefore, we have seen the develop also, right? We have seen the position function as a curve, and we got able to approach the average velocity during a time into an instantaneous velocity such to make the change of time approach to zero, right? To yield to zero, that we get the velocity is the change of position, which is instantaneous velocity is the collection of derivative of the position. Right, so any change referring to derivative for the change of time is little. And then acceleration. In other words, is the a of t is the derivative of velocity. Right? Acceleration by definition is change of velocity over time. That's similarly, but without loss of generality. Right? We have change of position is velocity, change of velocity is acceleration. Therefore, the acceleration will be the first derivative of the velocity, which is the first derivative of position. That sounds weird. The first derivative of the first derivative of position, which is we differentiate the position twice. We call that second derivative. Or double prime, right? So we have s double prime of t is the velocity, prime is the acceleration. So double prime of position is first prime of velocity is acceleration. So we usually say first order of derivative to be just the derivative of the function, but any higher order derivative such that the derivative of position is, we call that second derivative of the position, or it could be higher than third derivative, fourth derivative, fifth derivative, and so on. How we write it? Higher order, first derivative, second order of derivative, third order, we still use prime, double prime, triple prime, we're able to use. But for the higher order, we use parentheses. Fourth derivative, we use parentheses of 4. For nth derivative, for n bigger than or equal to 4, we use just parentheses around our n. The notation is similar for the function first derivative, second derivative of, or n derivative of x. Double prime of x is the most commonly used. Triple prime, fourth prime, nth derivative, that is nth derivative. Or sometimes we also use nth derivative of y respect to x. Second derivative is same, we use number d2y over dx squared. Or dn over dx to the n of f of x, that's another notation. Or d respect to x of f of x, have the nth derivative. Right? Subscript shows which one respect to, superscript to show that is how much differentiate, how many times of differentiate we do. Right, like here dny over dxn, dn over dxn of fx. Right, that sometimes we may see, right, but not that much commonly used as the first. We use this much, we use this notation much, but not a lot for the remaining notation, right? Not much for those. We use double prime of y, double prime of x, and derivative of fx, and derivative of y. This one may be, right, not much, and the remaining, that we may not use that much frequent as what we had. So that is higher order derivatives. Make sure you understand it, right? Up to cubic, up to 3 times differentiate, we use primes. Higher than that, it's hard to make primes like usual, right? We just to put a parenthesis around to be distinguished between the f square of x or second derivative, like 5 times, that is f of x to the 5th power, like trig functions. It may some people write it that way, and we put in parentheses means that is to differentiate 5 times, a little different thing. Right, anyway. And the velocity function is 100t over 2t plus 15 for an automobile starting from rest, which means time is bigger than or equal to 0. Right, we have velocity function in feet per second. Find the acceleration. The unit is feet per second squared. At different time. So we do that by finding the acceleration function first, then we just substitute the time in there, we'll be able to get acceleration. Right, so acceleration function is the derivative of velocity function. Then we can apply the rule that u equal 100t, v is 2t plus 15, where u prime is 100, v prime is 2. Right. One can apply that, and since that is quotient, so we use quotient rule, that we get u prime times v minus v prime times u over the square of v. Get 200t plus 1500 minus 200t over 2t plus 15 squared. That we get the acceleration to be 1500 over 2t plus 15 squared. To write it a little more clear, 2t plus 15 squared. Right, so for 5 seconds, 10 seconds, 20 seconds, the acceleration, nothing else but just substitute the time in there. Two times 5 is 10 plus 15 is 25. When we square it, that's 625. That is 12 over 5, or simply divide it. That's 2.4 feet per second squared. And in 10 seconds, we put A of 10. 1500 over 2 times 10 plus 15 squared. I'll get 35, which will be 1225. That is 60 over 49. Which is about 1.12. Well, we'll see that the acceleration will yield to 0 for the infinity amount of time. We'll see the velocity will yield to 50 feet per second as the time goes over or goes longer and longer, right? As the time flows. But the acceleration will yield to 0 as time passes. We got 40 plus 5, that's 50, and 55, right? 40 plus 15, that's 55. 55 squared, that's what? 3025. That's 0.496. For the acceleration. Right, so just we find the acceleration function by the quotient rule, and then acceleration at time, we just substitute the time into the acceleration function. What we can observe from the velocity and from the acceleration are simply I had mentioned already, right? So find the double prime. Well, this one is simply not that hard, right? So we get second derivative means apply the derivative twice. I do the derivative or differentiate the function twice. So f prime of x will be 2 times 2x plus e to the x, that is 4x plus e to the x. Then f double prime of x, you could omit that step, but that is the derivative of f prime of x by definition, right? So we take the we differentiate the first derivative, which is 4 plus e to the x, or 4 times 1 plus e to the x. Right, and that is our straightforward example. Then we see the next one, maybe a little bit more work to do. Right? We have e to the x over x. And f prime of x, to be found, use the quotient rule. Right? So first of all, u equal e to the x, v is x, u prime is also e to the x, v prime is 1. Right? So we get f prime of x, u prime times v minus v prime times u over v squared. That is e to the x times x minus e to the x over x squared. Right, this one, if we are, even though we factor out x e to the x, or even though we factor out e to the x, that nothing will help us, right? We still need to find the derivative of both of them. But one thing we can see is, well, if we separate them, that we get e to the x over x minus e to the x over x squared. Maybe a little bit helpful when we find f double prime, since we have one format of e to the x over x, its derivative. Right, but still maybe not that much beneficial. Right, so could leave it like that. Then to find f double prime of x, we get u is x e to the x minus e to the x, v is x squared. Well, for the u, that's also a large step, right? U prime will be the product. We get u prime times v plus v prime times u minus e to the x. Right, so if we simplify this a little more, right, so for x e to the x, I could separate it into another format, v prime equal e to the x. Therefore, x e to the x derivative is e to the x plus x e to the x. Right, in that step in the middle, therefore our u prime is e to the x plus x e to the x minus e to the x. That is still x e to the x. Our v prime is 2x. A little trick here in that one. Then f double prime, we get is u prime times v minus v prime times u over the square of x squared. That we get, well, x cubed e to the x minus 2x squared e to the x plus 2x e to the x over x to the fourth. And we can factor the x on the numerator out. Minus 2x e to the x plus 2e to the x over x to the fourth. That is, even though we factor out e to the x, that will not help us that much. So we could leave like that. X squared e to the x minus 2x e to the x plus 2e to the x. That is second derivative of this one, which is tricky enough, right? If we get more familiar with the product rule, then we could omit that small steps. But to write it out is still will be helpless, just to be not to be confused what we are doing. So we still left over some small, maybe 2 examples, then we'll move on to the next section. Right, so section 3.4. Right, so for today, for this time, let's just stop here. Right, so we get ready or practice more about the quotient rule, product rule, and higher order differentiation. So try more exercise, or try to redo our things we had done. Right, so try them. And next one will be called the chain rule. Right, so the issue we had seen about the differentiate of secant, we'll kind of resolve that issue next time. Right, so that's it for this section. For today's session. We leave some small things for next time.